Hey there, in this video we are introducing the linked list abstract data type, and this covers sections 17.1 and 17.2 in the Gaddis textbook. So as we continue our preview of a formal data structures course, we are looking for different ways of storing and managing lots of data. And of course, your first tool for storing lots of data is of course an array. That is the basic way you store a bunch of data in any programming language. Very powerful, but not perfect. Among the restrictions that an array has, it's one contiguous block of memory. When you declare an array, it is one connected component in memory, and you need a large enough space in memory to hold that. Sometimes, memory will be partly used up. You have a bunch of separate free components, but there's no particular place to fit your really huge array that you need right now. Two, a normal array is fixed size. It's this size, and you can't change it after you have compiled your program. Three, you can't add or insert stuff in a normal array, so that's not great. Now, of course, some people will say, well, I could just use a vector. But as we saw in the last video, a vector actually is just an array in disguise. The technical term for that is a dynamic array. And of course, you can dynamically allocate a larger array when you need to, but then you've got the issues of you're wasting, half the time, you're wasting half the space because it's a partially filled array. And then when it does grow, you have to copy all the elements over, and that's going to waste quite a bit of time on the CPU. So, use it, it's great, still not perfect. So in this video, we're going to see a totally different way of storing a bunch of data that avoids all of those particular issues with arrays, and that's what the linked list does for you. Totally different thought process to storing data. Let's look at this. Okay, so a linked list is going to be a set of data structures that contain references to other data structures. So this relies very heavily on pointers and dynamically allocating memory that we first saw in chapter 9. So each of the elements in your linked list is going to be one node at a time. And when we say node, it contains two things. Contains data. Okay, here's the thing you're actually trying to store, one unit of information. Could be an integer, could be a structure, could be a whole class object, could be a student object, an inventory item object, a feed inches object, right? One unit of data. That's the first thing in your node. And the second thing in your node is it's got a pointer to the address of another node. Going to point to the address of where the next node in the chain is. And so what we're going to be doing here is if you want 100 items to be stored instead of an array where you declare and you allocate the whole 100 item list at once, we're just going to be dynamically allocating one of these things at a time. So you add more stuff, dynamically allocate one node at a time, and that's going to be very different from how we set up an array with the whole thing up front. Okay, so here's what the whole linked list is going to look like. A linked list is a chain of these nodes with each pointer linked to the next node in the list, right? So this is what it's going to look like in memory here. Whereas an array is all connected, contiguous in memory, these nodes could be scattered around in different parts of memory. That'll be perfectly fine, happens quite a bit. Now, the start of the linked list, you'll need one special pointer that we refer to as the list head that holds the address of the first node. We call that the list head of where's the beginning of your list. And then there's also a special thing at the end of the list. The last node's pointer will be set to null pointer. Remember, that's really address 0, indicating a pointer not pointing at anything for real in C++. So the last node, you'll have the pointer set to null pointer as a sentinel for the fact that there's no more data after me in the list. So if you think about it, right, the contrast here is arrays, you might say, are count controlled. When you make an array, you have to know in advance how many things you need. And you're going to have a constant or a variable for how many things you put in that array. You normally process arrays with a for loop because you'll need to know how many things are there in advance. Now, with a linked list, this comes around the other way. It's basically sentinel controlled data. You're not going to be recording how many things there are because that doesn't really do you any good with a linked list, but you have this special marker at the end of the last pointer has null pointer, or really 0, or in older C++, that would be null. indicating that this is the end of the data. And so maybe you can anticipate that when we're processing linked lists, we're not going to be using for loops. We'll have to use while loops to scan for this null pointer at the end. Hopefully that echoes a number of things that we said in first semester programming about count controlled data versus sentinel controlled data. And so here's a really good example of that is arrays will be processing like it's count controlled data, and linked list you'll be processing with a whole lot of while loops because it's basically sentinel controlled data. Okay, there's the basic idea of a linked list. So let's think about the operations that a linked list should be able to do for us. When we started this part of the course in chapter 16, we said with any new abstract data type, we ought to be able to define what types of data can go into it. And you know what, for a linked list, the type will be anything. You can actually store any type of data you want whatsoever. And the second thing is define what type of operations that abstract data type should be able to do. So here's the answer to that for linked lists. The basic operations you normally see for a linked list are you ought to be able to append a node to the end of the list, add one new thing to the end of the list. You know, you can do that with a partially filled array, pretty easy, but you'll see that in some sense it's actually easier with a linked list. Now, you should be able to insert a node within the list. That's something that's very, very complicated if you try with an array, but you'll see here it's really no problem at all with a linked list. You ought to be able to traverse the linked list, right? Look at every single node in it and either, inspect it or print it or compare it or do math with it, right? You will have to process everything in the list from time to time. You ought to be able to delete a node, remove an item, and make the list get smaller, which is not something you can do with a standard array. And of course, we'll have to be able to destroy or clean up the list when you're entirely done with it. So we'll build out and think about how we would do all 5 of those operations in the rest of this video here. Okay, so for starters, here, the book provides a couple examples of linked lists, and here is the simplest one they call the number list. So this here is a linked list that just stores doubles. Double precision float values is what this is built for. So you have a complete code for this in the Gaddis book, and you should look at that. Right here, we're just looking at the header file that defines what this number list does for us. So it's a class called NumberList. And here's what the node structure is like in the private part of the class, because this is not something that an application programmer needs to worry about. They just send in some data. But from the perspective of the class programmer, we're defining what one node looks like here in the private part. And this might be among the most important things in this video, actually. You might want to pause the video and actually jot this down on a piece of paper, or maybe make a UML diagram out of this to refer back to just what is the structure of one node. So we have a struct here called list node. And like we said, here's the 2 things. First thing, here's the data. In this particular case, it is a double precision float that's called value. And the second thing here, look at this, the second thing is a list node pointer. A pointer to one of these things, a pointer to a list node, which we're defining right now. It's a little bit amazing that this actually works, that you can define a pointer to a thing that you're not done defining yet, but this actually does work in C++. So you have a list node pointer, and that's called next. Right? Whenever we see next in the rest of this video, we're talking about a list node pointer holding the address to the next list node. So again, maybe pause the video here, jot this down so you can refer back to it. List nodes do have 2 things in them, the value, which is the data, and next, which is the pointer to the next list node. Okay, so once you've defined that particular structure, as we said, you need one special pointer of where the list starts. Again, this is in the private part of our class. So here on line 15, you have a list node pointer called head, and that's the address of where the first actual node is. Okay, it's the stuff in the private part, right? That's stuff that the class programmer is going to be handling. Let's look at the public part. So as expected, you have a constructor, and what the constructor does is just sets head to null pointer. And of course, that's the signal that currently you don't have any nodes in your list when you first create it. You're going to have a destructor that we'll talk about a little bit later that's going to get rid of all the nodes. And then here's the other operations to append a node, insert a node, delete a node, and then we also have a function here to display the whole list to the screen. Notice that, append, insert, and delete all take in one double, and that would be one double value that you would like to store in your list, or in the case of delete node, to remove from the list, because that's the kind of thing that this particular list stores. And then display list there will have to traverse the whole list just to print stuff out and see what's in there. All right, so let's dig into the details about this. Again, follow along in the book, and you can see the specific code that does everything we're talking about here. And all of this is, I think, very interesting. So first of all, let's talk about traversing a linked list, because this is a job that you're probably going to have to do in all of those functions, as a matter of fact. And the idea here is you want to inspect and use and process everything in your list. The analogy would be like the for loop that you normally use to process an array, right? It's very standard with an array. You have a for loop, you're going to look at everything in the array, you're going to print it out or get input or add it to an accumulator or something like that. So this is what we're trying to do here with a linked list. Visit each node in the list and either display it or validate it or add it together or something. So the basic process here, as we said, you're not going to be using a for loop, you're going to be using a while loop. So you start off, you make a new pointer, you set the pointer to the contents of the head pointer, basically just copy in the address that's sitting in head. Then you'll have a while loop, and the while controller will be while the pointer is not null pointer. Apparently there's more nodes to come. Then process the data in the node that you're actually looking at right now. Okay, and then once you've done that, go to the next node by setting this pointer that I'm talking about to the contents of this node's next pointer, right? Because you're looking at a node and it's got a value, you deal with that. It's got a pointer to the next node, so you just copy that address into this loop controlling pointer and then go back to the while statement. And while that pointer is not null pointer, process that data, get the next node. While that pointer is not null pointer, do the same thing. At some point, you'll run into that pointer at the end that is null pointer, and that gets you out of this while loop and you're done. So that's actually, the analogy of the for loop that you use for arrays. This is how you look at every single thing in a linked list, and this will be part of every single function that we're talking about here today. All right, let's kind of step through that. Let's kind of play act that. So here is a linked list. As you can see, that's linked up. It's got 5, 13, 19 in it. Again, these could be in widely disparate parts of memory, but the pointers are how you're going to find one or the next. So your while loop is going to have this pointer called node pointer, and the very first thing you do is you copy in the address from the list head into node pointer, and now effectively you're pointing at that node that's got the 5. Okay, so print that out, right, or do something with it. Print out the 5, you're done with it. Then whatever the address is in this next pointer, you copy that into node pointer, and now effectively node pointer is telling you where the 13 is in the memory system. So deal with a 13, copy this address into node pointer, right? Now you're looking at where the 19 is, okay? Deal with that, copy this address into node pointer, and now node pointer is holding null pointer, and that's what's going to get you out of the while loop. So hopefully that you get a visual sense of how that's going to work. Let's look at the actual code here. Okay, so here is the code in our NumberList example class in the Gaddis book here called display list. And the goal here is display list shows the value stored in each node of the linked list pointed to by head. Now, I would personally rip out all the comments here. I don't normally use one comment per statement. I actually think this makes this looks more complicated than it needs to be. So personally, I would rip out all the comments, and then this is really only a 5-line function. But let's think about how this works. So you make this node pointer, which is of type list node pointer, like we said. You initialize that to the address in head. So whatever's in the head address of your list object, you just copy this in node pointer. Here's the while loop controller on line 54. And you can see they've written that as while node pointer, very, very, very short. Now remember, null pointer, the thing at the end, is really just the number 0. And in C++, that counts as false. So as long as node pointer is holding anything else, any other address than 0, the null pointer, right, it's going to be some positive number, which C++ counts as true, and therefore you're going to get into this while body, do it, and come back. right? Do it and come back, do it and come back. Once node pointer is actually holding null pointer, otherwise known as 0, that's going to count as false and get you out of this loop. Now, alternatively, that line 55, you could have written that, and some people do. They write that says, while node pointer is not equal to null pointer. And that does the exact same thing. On the one hand, it's a little bit longer, so it's not my preference, but some people consider that to be more readable, more visually readable, so you can do that if you prefer, right? While node pointer is not equal to null pointer. I mean, that is literally what we said in the pseudocode 2 slides ago, so you could do that. I tend to do this the same way the book is doing this, again, because I like things to be short. Now, what's happening in that while loop is, like we said, 2 things. Number 1, on line 57, you're going to use the data that you're looking at. So remember, every node has 2 fields, right? There's a value and there's next. So from this node pointer, right, use the arrow syntax, get the value data, and in this case, print it out. Or in other cases, we'll be doing math or adding or something like that. Once you've done that, then you're going to use this node pointer's next value. Of course, that's the address to the next node. Take that address and copy it into this node pointer that's controlling your while loop. So I feel like the really magic thing about this is this line 60. And, you know, maybe it's a good idea to possibly pause the video and just really think about how line 60 is working and reflect on that. And once you really understand that line 60, right, you really understand how we always process linked lists, right? Take the node pointer's next address, copy it in a node pointer, and go back to your while loop on line 54. Right, and it happens again and again and again until you hit the one at the end that's holding null pointer, and then you're done with this function. Pretty interesting. Okay, let's talk about some other functions, right? Appending a node. And that means, again, adding a node specifically to the end of the list. That's what append means, adding specifically to the end. So your basic process here is you're going to dynamically allocate a new node. We said you dynamically allocate one node at a time. So do that. And then you have to link it up in the right place in the list, which is to say the end of the list. So check out the head pointer. If the head pointer is pointing at null pointer, which is to say the list is empty, well, this is your very first node apparently. Just point the head pointer to this new node. Okay, and then you've got this one single thing. Okay. Most of the time, you'll have other nodes in the list already. So in that case, you're going to have to traverse the list to the end, like we were just talking about with the traverse the list function. Okay, so you'll need a while loop, find the end, find the node that's got null pointer, and then set that pointer to this new node that you just dynamically allocated. And then the thing that you just made, the new thing, will be linked in at the end of the list, which is where you wanted it. Great. Okay, so let's play through this. I'm not going to show the code for every single one of these functions in this video. I think that would probably be too long. But the book, of course, has complete code to all this stuff. So feel free to look at the details in the book, and we'll just kind of hand trace what this would look like. Want to append a node. Now, before I got to this point in this illustration here, a couple things have already happened. I have a linked list, actually the same one we were talking about before, that's got 5, 13, and 19 in it. And what I want to do is I want to add the number 23 to this list. So before we've even pulled up this illustration, we've dynamically allocated a new node that's holding 23. So here's new node pointer, dynamically allocating thing, put a 23 in for the value, put null pointer in for the next pointer. Okay, so you've set up your additional node here dynamically. Second thing we've done, and this is all in what I'm calling step 1 here, is we've traversed the list to find where the end is. So you have a node pointer, you had a while loop, and you looked at the 5. Is that the end? No. Is the 13 the end? No. Is the 19 the end? Yes, because it's got the null pointer in the next value. Okay, so this has all happened first. That's what I'm calling step 1 here. We've allocated a new node, and we've located the end of the list. And now step 2 is the magic is, right? Whereas for, like, if you had a dynamic array like a vector, you'd have to make a brand new array and you'd have to copy all the stuff over. But for a linked list, look how easy this is. All you got to do is go to the next address in this node that's holding 19 and just point it at your new node. That's it. It's just one step. As easy as that. And now this linked list is telling we have a 5 followed by 13 followed by 19 followed by 23, and that's the end because it's got that null pointer there, right? Just one step, as easy as that, as opposed to what a vector has to do, which is an enormous amount of work to make an array grow. So much simpler. Now, admittedly, we did have to dynamically allocate a node, and we did have to traverse the list to find the end, so that was a little bit of work. But once you've done that, just one more thing, just change that pointer to link it up. So clever. What else? Okay, so here's something you can't do with a normal array without a whole lot of work: inserting a node into a linked list. So you don't have to just put nodes at the end. You can actually put it wherever you want in the linked list. It's pretty easy to do that. And the interesting thing is the way that this example in the book is set up is that the insert value function automatically keeps everything in the linked list sorted in order. So you may not need a sorting function on linked lists like we needed for arrays back in chapter 8, because you're only adding one thing at a time, and it's fairly easy to keep the one thing in order with the rest of the list. So, instead of having a master sorting function, just every time you add one thing, put it in the right order, and that's how the book has set up their insert function. So let's see how this works. So you have a new value, you make a new node, right? Dynamically allocate the new node. Now, where does it go? So what you're going to do is you have 2 pointers here to do the list traversal. And you have one point, the main pointer in your while loop, of course, that's going to scan for the right place to put the new node. You're looking for the first value that's bigger than the one you're trying to add. You have this pointer to locate the node with the first data value that is greater than the node that's being inserted. And in addition to that, you have a following pointer that's just holding whatever the last thing the main pointer had. You have this pointer to trail behind by one node to point at the node right before the point of insertion. So when you've done this here, you're tracking both the thing that comes right after your new node and the one that comes right before it, and that's how you're going to link it in the right place. Right? So your new node will be inserted between the nodes pointed at these 2 pointers here that I'm talking about. Let's hand trace that. Okay, so here we have our 5, 13, 19 linked list. Okay, and what we want to do here is I want to insert the number 17 and still keep this list sorted. So again, before we pulled up this illustration, we've dynamically allocated a new node, right? We set the value to 17 and we set the next to null pointer, as you do when you make a new node. And we've also traversed the list to find the right place to insert it, right? This node pointer that's controlling your while loop here, it's asking the question, have I found a value greater than what I'm inserting? So first of all, it looked at the 5. It said, is that greater than my 17? Well, no. So go on to the next node. 13, is that greater than what I'm inserting? Well, no. So went on to the 19, is that greater than what I'm inserting? Well, yes. So apparently this is the thing right after what I'm inserting. And then every step along the way, like we say, we have this previous node that just takes a copy of the last thing that node pointer used to have. So you've got node pointer pointing at the 19 node and previous node pointing at the 13 node. Okay, so a little bit of a traversal, no problem. And now, so that's what I'm calling step 1. We've done all that stuff. And now step 2, you just have to hook up the pointers to get the 17 in the right location. Again, just 2 steps here. So the address, the next address of the 13 node, you aim that at this new node that's holding 17, and symmetric to that, the next address in the 17 node, you just have to point that over at the 19, and now you've got it hooked up in the right place. Let's see that happen. Bam. Easy as that. There's no big copy job, right? You don't have to move around all the other nodes. It's just 2 pointers that you're updating. The one from the 13 to this new node, and the one from this new node to the one that came right after that. And now you have a linked list that's saying I've got 5 followed by 13, followed by 17, followed by 19, and that's the end. And you notice that linked list is entirely in the right order. Great. So easy. Doesn't take very much time on the CPU, not wasting any space really. Fantastic, right? Don't even need a sorting function because you're just adding one thing at a time and it's always in order. Fantastic. Okay, so now let's start to clean stuff up. At some point, you're done with your list. You want to remove one of the elements. That's what we're calling the deleting a node function, and this is what you use to remove a node from a linked list. Maybe you can anticipate what this is going to look like. So if the list is using dynamic memory, and it is, I mean, that's the whole point to why we're doing this, then you're going to delete the node from memory like you have to so you don't have a memory leak. And again, very similar to the insertion of a node, you're going to have two pointers in this function. You're going to traverse the list, find the value that you want to remove, and then what you do is basically just hook up the pointers around it, delete that node, and now you have a linked list without that one thing. Take a look at that. Okay, so kind of hand tracing this. So what I have here is I have a linked list that's holding 5, 13, 19, and I would like to delete the number 13. Okay, so step one, we had a traversal process with our standard while loop, and it looked at the 5 and said, is that what I want to delete? Well, no, because I want 13. And it moved on to the 30. Is that what I want to delete? Well, yes. Okay, so that's called step one. That's what I'm calling step one on this slide. And again, you have this previous node pointer that's just holding a copy of what node pointer was holding 1 second ago. So it's pointing one node before here. And so we found what we want to delete, this 13. So you go into step 2 here, and we adjust the pointer right before it around the node we want to delete. So this next pointer in the 5 node, what you're going to do is you're going to copy in the address from the 13 node. Okay, so take the address from the 13 node, copy it in to the next pointer for 5, and now effectively you've got the 5 node pointing over at the 19, because that's what the 13 was pointing at, right? So you've got that, that's step 2, and now you've done that, all you have to do is just delete the memory of the node that you want. So whatever, you just do delete node pointer, and it's gone. Great, so you've cleaned up that memory, you could use it for something else, and now you have a linked list that's saying I've got a 5 followed by a 19, that's the end. And once again, it's just a little bit of magic by just doing some pointer stuff, right? Not spending a lot of time on the CPU, that was really just 2 pointer things happening there, and you've deleted a node. Fantastic. Okay, now there's a destructor, right? So of course you have a linked list, you've added as many things as you want to, 100 things or 1,000 things, that's great. Of course, when the linked list goes out of scope, you have to clean up all of those nodes, and that's what the destructor is there for. So that's what this is right here is what's going to happen in the destructor. You've got to delete all those nodes one at a time, right, one after the other, to get rid of the linked list and clean it up out of the memory. So to do this, again, you're going to have one of those traversal while loops. You're going to scan every single node, and as you look at every single node, you have to unlink the node from the list. Basically, you do that delete job on every single thing, unlink it from the list, and then using dynamic memory, which is what I would expect to do, free that node's memory, and then go on to the next one. Okay? And then the last thing is you've got rid of all the nodes, and don't forget, when you have an empty list, the head ought to have the value null pointer to tell us that there's nothing in the list. So, you know, I'm going to put this, what we're going to see the book do is put this function in the destructor, which makes sense. But you could also have like a separate public function. It doesn't have to be in the destructor. You could have a separate function that says like clean up the list that does this. And if that happens, then maybe your application programmer wants to use the linked list to add some more stuff later on. And at that point, you would need it set up for that situation with head pointing to null pointer like it got initially constructed as. Okay, but I think in the book here, this is just in the destructor, and the whole list is just going to be gone right after you do this. So basically just do that on every single node and delete them all. Great, and that's what you need in the destructor. Okay, so there is our, you know, very quick preview at the magic of linked lists. What, you know, the first time I ever saw this, my mind was blown, and I totally wanted to code this up myself just to prove that this is even possible with the pointers and the dynamically allocated memory. So amazing, you know, and I'm still kind of amazed by it. Again, we kind of hand traced the operation so you get a feel for what's happening there. I'd say, you know, dig into the source code that's in the book and, you know, see the specifics of all these functions we were talking about here. So let's kind of wrap up by comparing linked lists versus arrays. And these are your two primary ways of storing lots of data. They're not the only ways, but probably the primary ways that you have to choose to store lots of data in your data structures course. It'll probably be coming up pretty soon. So the advantages of linked lists is, like we're saying, you can easily grow and shrink in size because you're just allocating one single node at a time and linking it into the right place, or deleting one node at a time and just changing one pointer to make that happen. It's a lot faster to insert items at the start or the middle of your list. I mean, for a fixed array, that's totally impossible. For a partially filled dynamic array, you actually could insert items, but you'd have to copy all the other elements up by one slot. And again, if you have a large array, that's going to take a long time on the CPU. Linked list, one thing, just change one pointer. Great. You can save space over partially filled arrays. Again, if I have a partially filled array that's holding a large structure type or a large object type, half the time you're wasting half the space. And that could be quite a lot of memory. Linked lists will never do that. You'll never have wasted nodes. Every node is holding one unit of data that you really wanted to record. So you can save space specifically over the partially filled or dynamic array situations like a vector, for example. But it's not perfect, okay? So some disadvantages are that it may be slower. It's going to be slower to access elements because you need to do that traversal process, right? Arrays, you can jump to any element in the array instantly anytime you want using the subscript notation. If you think back to chapter 9, when we talked about what's really happening when you write down array square brackets, right? It's really an addition. You take the address of where the array starts, you just add how many steps into it you want to go, and then you can immediately just jump to that address in one step. Practically no time at all. Well, with linked lists, you can't do that because the nodes could be anywhere in memory and you can't just predict where it is. You do have to do this traversal process of one node after another, after another, after another to find all the stuff in the list. And for example, the append operation did have to scan the entire linked list to find the end to find out where to put the new node. So that actually will be slower than what arrays do. Now, linked lists will be saving you space versus partially filled arrays, is what we said at the top, but it will be using more space versus a fixed size array. Why? Because of the pointers, right? You've got the data that you're storing, but then every single piece of data also had to have a pointer attached to it for the linking operation, and that's something that an array doesn't need. Now, a pointer is not very large. Like on our system, it's only 8 bytes. It's not a lot of space, but arrays don't need that at all. So admittedly, if you knew in advance exactly how many things you would need, in that case, you ought to still use a fixed size array because then you don't need the pointers there and you're saving space over the linked list. But again, if you don't know how many things you need, then a linked list is probably a better option. Other thing that pains me about the linked list is that you cannot use the binary search method, right? That super fast method back in chapter 8 of very quickly finding something in an array. Binary search worked, if you remember back in chapter 8, by jumping into the middle of the array and then deciding whether you should go to the beginning part or the ending part for the next jump to the middle part of that, and so on and so forth. Well, the problem with linked lists is you can't jump into the middle of it because you needed to do the traversal process. So that whole trick to binary search is just broken and you totally can't use that on a linked list. So as usual, some advantages and some disadvantages, some pros and cons. And you should be selective about which storage technique you use depending on the application that you're building. So the linked list is probably ideal in situations where we're receiving an unknown amount of input data, maybe from a user, maybe reading from a file, maybe receiving it from a network. And again, if you don't know how much data you're going to have in advance, linked list is really good. Linked list is probably, arguably better maybe than a dynamic array or a vector. But if you do know how much stuff is coming in to begin with, you already know how much stuff there will be, then you should probably use a fixed size array, and that would in fact be better and more efficient. And then of course, there's this issue of here, you can't use the binary search method. You can keep it sorted really easy. We saw that the way the insert function is set up, but you can't use the binary search method. So that kind of hurts me a little bit. So maybe we should be on the lookout as we go forward. We should be on the lookout for maybe some other data structures that maybe has the best of both worlds. Maybe is fast with binary search like an array, but is not wasting any space and is easy to insert and add elements. Maybe there's some data structure that kind of has the best of both worlds, and we'll be on the lookout for that as we again preview a data structures course in future videos. So we'll be thinking about that. So I would, after this introduction to the magic of the linked list data structure, I'd meet with my students and do this lab and pull up that NumberList example out of the book and write a test driver as do. So read the specification, make sure we understand it, how we can create a number list, how we can construct it, test all of those functions we were talking about, confirm we know what to expect from the append and the insertion and the deletion and how to display it and things like that. And if we have any questions about it, that's a good opportunity to actually dig into the source code and actually see what's happening there. So, save some numbers, delete some numbers, print it out, be able to predict what's about to happen. And I think that's a good lab just to get accustomed to using linked lists. This is not something here where we have to write our own code to make it happen. It's all provided by the book, but just using it is a good start there. Okay, so good introduction to the basics of linked lists. Those operations are what's probably be part of any linked list class. But that's not the end of the story. So in the next video, we're going to be looking at some variations on the linked list, some alternatives of how you could set it up that might possibly improve on some of those disadvantages we were talking about. But then again, maybe they're going to weaken some of the advantages. So a couple other options on our menu of ways you could do that. And we should probably also think about having a linked list that stores something other than just doubles. So that's what's going to happen in the next video. So hopefully that sounds interesting, and I'll see you then for that.